You know, it is, it's a funny thing about human nature. When you're driving down a highway, maybe somewhere in the American Midwest, or passing through the vast expanse of the Central Valley in California, you look at the window and you see these massive, perfectly flat fields.
Oh, yeah, just stretching all the way out to the horizon line.
Exactly. And what does your brain naturally do? Your brain just accepts it. You think, wow, look at that flat landscape. Nature sure has a neat, orderly way about her.
Right, we just assume it's always been that way.
But the truth, the absolute mind-bending truth of what you are looking at is that almost none of that flatness is natural.
Yeah.
That perfectly flat farmland is actually one of the oldest, most consequential, and intensely engineered human achievements on the planet.
It really is one of the greatest illusions of the modern world.
Yeah.
We look at a farm and we immediately see biology, right? We see seeds, we see soil, we see plants photosynthesizing and growing. But before any of that biology can happen at a commercial scale or, with any kind of agricultural efficiency, there is a massive foundation of physics and civil engineering that has to be violently laid down first.
Yeah.
You're looking at reshaped Earth.
Which brings us to the mission of our deep dive today. We are exploring the hidden mechanics of how we completely reshape the Earth to feed ourselves. And we have an incredible stack of sources we're pulling from for this.
Yeah, we really do.
We have a comprehensive research report that traces the entire history of agricultural land leveling. It starts all the way back in ancient Mesopotamia and carries us to the dawn of the Laser Age in the 1960s.
And supporting this, we have a deeply detailed bibliography of federal records, old university agricultural extension publications, equipment manufacturer histories.
Even the actual granular patent filings from the mid-20th century, which are wild to look at.
They really are. And to give you a clear framework before we jump into the timeline, when we use the term agricultural land leveling, we are talking about a highly specific engineered process.
Right. It's not just dragging a rake over the dirt.
No, not at all. It is the practice of reshaping a field surface to precise, mathematically calculated grades. And the goal is singular. It's to allow for efficient irrigation.
To control the water.
Exactly. The central theme running through every single source we have today is that humanity has been engaged in a relentless 6,000-year struggle to control the flow of water on agricultural land. To control the water, you must first master the earth it sits upon.
Okay, let's unpack this, because to truly appreciate the massive, laser-guided hydraulic machinery of the 20th century, we have to shift our perspective away from the modern grocery store and go all the way back to the ancient past.
Right, back to the beginning.
Yeah, why does a perfectly flat field even matter so much in the first place? I mean, rain falls on hillsides just fine.
Well, it all comes down to the unforgiving physics of gravity, water, and soil capillarity. If you are relying on surface irrigation, which historically is how almost all of human agriculture has been sustained before modern pressurized sprinkler systems, you need a uniform slope.
Because water is basically a lazy element, right?
That's a great way to put it. It will always seek the path of least resistance. So if a field isn't perfectly leveled or graded to a very specific, consistent incline, the water simply doesn't behave the way a farmer needs it to.
It's just going to follow gravity down to the lowest possible point.
Precisely. It pools in the low spots. And when water pools, it doesn't just sit there innocuously. It actually drowns the root systems of the crops in that depression, suffocating them by cutting off soil oxygen.
Oh, wow.
Yeah, and conversely, because the water rushed past the slightly elevated areas of the field to get to that low spot, those higher crops are completely bypassed. They get no water, and they wither and die.
So they're starving while the others are drowning.
Exactly. Land leveling and the history of surface irrigation are completely inseparable. You cannot successfully execute one without having done the other.
Think of it like trying to evenly coat a completely warped antique dining table with a single cup of water. If that table is covered in dents and divots and warped bumps, and you pour that cup of water out, it's just going to puddle deep in the dents and leave the rest of the wood totally dry.
That is a perfect visual.
Right. You can't just magically command the water to spread an even millimeter thick across a bumpy surface. You only have two options. Either you need way more water to flood the entire thing, which is massively wasteful.
Very wasteful.
Or you have to physically sand the entire table down until it is mathematically flat.
And that analogy captures the physics perfectly. And ancient civilizations understood this sanding down process intimately, out of pure survival necessity.
We had to.
Yeah, If we look at the historical record for Mesopotamia, around 6000 BCE, farmers along the Tigris and Euphrates rivers were constructing these incredibly elaborate basin irrigation systems.
Because that area didn't get much rain, right?
Almost none. Southern Mesopotamia received almost no rainfall. Controlled flooding from the rivers was the absolute only way to grow food and survive. And they had to grade those fields precisely so the gravity-fed water would distribute evenly across the basin.
And the sources mention that this wasn't just like a casual suggestion among farmers. This was actually codified into law.
Yes, and this is where it gets into the societal impact. If we look at the Code of Hammurabi, which dates back to roughly 1750 BCE, there are actual laws penalizing farmers whose poorly leveled, ill-maintained basins ended up flooding their neighbor's land.
That is fascinating. So if I'm a Babylonian farmer and I do a terrible job grading my field, the water breaks out of my basin, floods your wheat, and ruins your crop. I'm legally liable for that because my earthwork was sloppy.
It was a serious matter of civil liability nearly 4,000 years ago.
Wow.
Yeah, the state recognized that the survival of the community depended on every individual farmer maintaining strict geometric control over their land. And we see similar imperatives in ancient Egypt.
Capturing the Nile floods, right?
Right. Capturing the nutrient-rich silt from the predictable annual Nile floods required incredibly precise earthen embankments and perfectly leveled basins to ensure the silt settled evenly across the planting area.
The tolerances required for some of these ancient crops just blow my mind. I mean, our sources talk about the monumental terraced paddies of China and Southeast Asia, which date back to roughly 9,000 BCE.
Oh, the rice paddies.
Yeah, we are talking about rice paddies that require water depth tolerances of just a few inches. If a paddy is uneven by even 3 inches from one side to the other, the rice won't grow properly.
The deep end drowns, the shallow end dries out.
Exactly. How on earth were they achieving a 3-inch elevation tolerance across a massive field thousands of years before surveying equipment existed?
It's brilliant, actually. They used the water itself as the ultimate leveling tool.
Oh, really?
Yeah. A farmer would build a rough berm, flood the enclosed area with a few inches of water, and then physically look at where the water wasn't covering the soil. That exposed soil was a high spot.
So simple, but so smart.
Right. They would wade into the mud, dig up that high spot with hand tools, and carry it in a basket to where the water was deepest. When the water was a perfectly uniform depth everywhere, the land beneath it was perfectly level.
That's incredible. And we see massive structural earth moving in the Americas, too, long before European contact. The pre-Columbian Andean civilizations were building massive, step-like agricultural terraces into impossibly steep mountain slopes, like 10,000 years ago.
Carving them right out of the rock.
Yeah. They were essentially carving flat, irrigable benches right out of the side of the Andes Mountains.
What's fascinating here is, for thousands upon thousands of years across all these radically different cultures, climates, and continents, the absolute only way to achieve this vital life-sustaining precision was through grueling, back-breaking human and animal labor.
Just pure muscle.
Pure muscle.
Mm.
We are talking about millions upon millions of human hours with wooden hoes, woven baskets, and sheer biological effort.
The caloric math of that ancient reality is just staggering when you stop to think about it. You are burning massive amounts of human calories doing heavy civil engineering, literally carrying baskets of wet mud on your back.
Just to grow the food you need to replenish the calories you just burned.
Exactly. It is a brutal biological loop. But that sheer limitation of human muscle brings us forward to a major turning point in our deep dive, the American West in the 19th century. Because when settlers pushed into places like California's Central Valley, they quickly realized that this ancient biological loop simply wasn't going to be enough to tame a continent of that scale.
No, it absolutely wasn't. The environment in the American West presented a fundamental shock to settlers coming from the eastern United States.
Because the East Coast is totally different.
Right. The East Coast gets regular, reliable rainfall. You can generally farm without massive irrigation infrastructure. The West, however, was arid or semi-arid.
Right, so you have to move the water.
Exactly. Gravity-fed irrigation, bringing water miles from a river via canals, was the only practical way to farm. And as we established with the physics of water, you simply cannot irrigate effectively without heavily leveled land.
And early American homesteaders were struggling intensely with this. The sources described them out in the blazing heat with basic hand tools, mattocks, hoes, shovels, trying to flatten acres of virgin terrain.
It was a nightmare.
They relied on animal-drawn slip scrapers, which were essentially just small metal or wooden scoops dragged by a team of mules. A guy would walk behind the scoop, tip it to bite into a high spot of dirt, and then the mules would drag that scoop to a low spot where the guy would muscle it over to dump the dirt.
And it was incredibly slow, agonizing work. The volumes of earth they needed to move to make these vast western valleys agriculturally viable were beyond the scope of those primitive slip scrapers.
And what were the other things they used? The drags?
Yes, the wooden drags. This was literally just a heavy timber plank, sometimes weighted down with rocks, dragged across plowed fields to try and smooth out the seed beds.
That doesn't sound very precise.
It wasn't. It didn't truly move earth from a high spot to a low spot in any calculated way. It basically just smashed the clods of dirt around. The agricultural expansion of the West was hitting a hard, physical bottleneck.
But then, enter a man named James Porteous.
Ah, yes.
He's a Scottish immigrant who arrives in the U.S. in 1873, and by 1877 he has established a wagon shop in Fresno, California, right in the heart of the Central Valley.
Porteous is a pivotal figure in this history. Being situated in Fresno, he saw firsthand this desperate, existential need for efficient canal construction and field leveling among the local farmers.
He saw the struggle.
He watched them exhausting their draft animals and themselves trying to prepare the land. He realized that the tools themselves needed a fundamental redesign.
So he gets to work, and he invents what becomes globally known as the Fresno scraper. He files a series of patents in 1882 and 1883. And looking at the patent drawings in our sources, the mechanics of this thing are brilliant. You don't have to be a mechanical engineer to appreciate why it was such a massive leap forward.
Not at all.
But how did the Fresno scraper actually solve the problem of the older slip scrapers? What was it doing differently?
It was an elegant leap forward in earth-moving geometry. Porteous started by looking at the common buck scraper, which was just a wide board used to push loose dirt.
Kind of like a snowplow.
Exactly like a snowplow. His first major improvement was adding a hinged tailboard to help control the flow of the dirt. But the true breakthrough came with his 1883 patent, which featured a C-shaped metal bowl.
Okay, why is a C shape so important for moving dirt?
Well, think about the physics of a flat blade versus a curved bowl. If you push a flat piece of wood or metal through dirt, the dirt just piles up in front of it and spills out over the sides.
You lose half your load while you're moving it.
Exactly. A C-shaped bowl, however, changes the dynamic. When the leading edge bites into the soil, the dirt is forced up and curls back into the curve of the bowl.
Oh, so it catches it.
It essentially loads itself and holds the soil in place. This allowed the implement to actually scoop the soil, carry it securely over a distance without spilling, and then, using a refined set of levers that the operator controlled, precisely dump it or spread it in a thin, controlled layer.
So instead of just blindly shoving a pile of dirt around, it's actually picking it up, transporting it, and laying it down exactly where the low spot needs it.
Yes.
The productivity stats on this simple horse-drawn invention are wild. The research indicates it quadrupled the volume of soil a single team of horses or mules could move in a day.
Quadrupled. Just by changing the shape of the metal.
One Fresno scraper, operated by one man and a team of horses, could move up to 225 cubic yards of earth in a single long day. And what really made it explode in popularity was the cost.
Right, it's very accessible.
A 2-horse model cost $28. A heavy-duty 4-horse model was $37.
And because of that combination of high efficiency and low cost, its impact went far beyond California agriculture. The Fresno scraper was mass-produced and shipped worldwide.
They used it everywhere.
They did. It went to agricultural projects in South America, India, Australia. It was heavily used in the construction of the Panama Canal, moving millions of yards of earth.
Wait, they used it in World War I too, right?
Yes, it even saw combat service with the U.S. Army in World War I, where it was used extensively for digging miles of trenches and rapidly leveling military airfields.
That is wild.
It was such a significant piece of technology that the American Society of Mechanical Engineers actually designated an International Historic Engineering Landmark in 1991.
It is kind of amazing to think that a $28 dirt scoop designed in a wagon shop gets a prestigious engineering landmark designation alongside things like suspension bridges and steam engines.
It really is.
But it makes perfect sense when you look at the macro picture of what was happening in America at the turn of the century. There was suddenly an astronomical volume of land that required leveling.
Yes, and that explosive demand was entirely driven by the federal government deciding to reshape the American landscape on a continental scale.
Enter Teddy Roosevelt.
Exactly. On June 17, 1902, President Theodore Roosevelt pushed through the Newlands Reclamation Act. This was a monumental piece of legislation that authorized federal funding for massive, unprecedented irrigation projects across 16 arid western states.
So the federal government is essentially stepping in to say, we have all this dry, unused land, and we are going to engineer it until the desert blooms.
That was the exact mindset. The act created the United States Reclamation Service, which later became the Bureau of Reclamation. And they didn't just build a few local canals. Over the following decades, they oversaw the construction of more than 600 dams.
600 dams.
They built reservoirs and tens of thousands of miles of major canal systems, ultimately providing irrigation for 10 million acres of land. To put that in perspective, today, that specific irrigated land produces roughly 60% of the nation's vegetables and 25% of its fruits and nuts.
But the critical connection here, the reason the Fresno scraper became so vital, is that you can't just build a massive concrete dam, run a water pipe to a bumpy natural field, and call it a day.
Nope. The water won't flow right.
Every single one of those 10 million acres that was scheduled to receive canal water first required grading. The introduction of all that new federal water created a massive, urgent, continental demand for perfectly leveled land.
It did. But, while the Fresno scraper was indeed a marvel, it still relied fundamentally on biological power. It was constrained by the physical limits of horses and mules.
They get tired.
They get exhausted.
Cool.
Animals require massive amounts of feed. They require rest. They get exhausted in the western heat, and they can only pull so much dead weight. The agriculture industry was hitting another ceiling.
But as the 20th century dawned, a new technology arrived to change the game entirely. The internal combustion engine.
A total paradigm shift.
Which kicks off the era of mechanization. In the early 1900s, companies like Holt Manufacturing and C.L. Best were experimenting with replacing wheels with tracks, developing the very first crawler tractors. In 1925, those two companies actually merged to form the Caterpillar Tractor Company.
A name everyone knows today.
Right. But why were crawler tracks so essential for this specific kind of farm work as opposed to just putting bigger wheels on a tractor?
It comes down to ground pressure and traction. Early wheeled tractors were heavy, and all that weight was concentrated on the small contact patch of 4 steel wheels.
So they just sink.
Exactly. If you took one of those into a socked, plowed agricultural field or tried to pull a heavy load of dirt, the wheels would simply spin, dig a rut, and sink to the axles.
That makes sense.
Crawler tracks, what we now call continuous tracks, spread the immense weight of the engine and chassis over a much larger surface area. It's the exact same principle as wearing snowshoes.
Ah, okay.
This allowed the tractors to stay on top of the soft soils while providing relentless, untiring pulling power. They were slow, typically moving at about 5 miles per hour while pulling a fully loaded scraper, but they never needed to stop and rest like a mule team.
Which brings us to a figure in our research stack who absolutely fascinated me, R.G. Letourneau.
Letourneau is a legend.
Our sources practically paint this guy as the Thomas Edison of moving dirt. He starts out in 1920 as just a humble land leveling contractor. He scrapes together enough money to buy a used Holt crawler tractor, and he goes to work in the dirt.
And he completely changes everything.
But within a few years, he completely revolutionizes the entire industry. What was the state of earth-moving machinery when Letourneau first sat down in that tractor, and what did he do to change it?
Well, Letourneau is truly a force of nature in the history of mechanical engineering. When he started in 1920, scrapers had grown much larger than the old horse-drawn Fresno models, but they were incredibly clumsy.
How so?
To operate a large tractor-drawn scraper, you needed 2 men. One man drove the tractor, while a second man rode on the scraper itself, physically pulling heavy, dangerous steel levers to engage the blade into the dirt, lift the bowl, and dump the load.
That sounds incredibly sketchy.
It was bone-jarring, exhausting work. Letourneau hated inefficiency, so in his very first year of contracting, he decided to fix it.
Just right away.
Right away. He installed an electrical generator on his tractor, ran wires back to the scraper, and installed electric motors on the scraper's mechanical linkages.
So he just invents the first single-operator, power-controlled scraper out of thin air.
Basically, yes.
He eliminates the need for the second guy pulling levers and controls the whole massive apparatus with switches right from the driver's seat.
Precisely. He brought electricity to raw earth moving. And he didn't stop there. In 1922, he developed a machine he called the Mountain Mover. This was revolutionary because it was the first completely welded scraper.
Wait, why is welding such a big deal here? Weren't they already using metal?
They were using steel, but it was riveted steel.
Oh, like old bridges.
Exactly like old bridges.
Yeah.
When you rivet steel plates together, you have to overlap the heavy plates, drill holes, and pound hot rivets through them. It makes the machinery incredibly heavy, and under the massive stress of ripping through hard-pan dirt, rivets shear off and fail.
Because there's so much tension.
Yes. Welding fuses the metal into a single continuous piece. It made Letourneau's equipment incredibly strong, yet surprisingly light compared to the older riveted behemoths. It meant the tractor's horsepower was being used to move dirt, not just drag heavy iron around.
And the timeline of his innovations just keeps accelerating. By 1932, he does something that the entire heavy machinery industry thought was completely insane.
Tires.
He takes the heavy steel wheels off his massive scrapers and puts pneumatic rubber tires on them. Why was that considered crazy, and why did it work?
Well, people thought rubber tires would simply shred under the immense weight and the sharp rocks found at excavation sites. Steel wheels were viewed as indestructible.
Right, it's just heavy metal.
But Letourneau understood physics. Steel wheels have terrible rolling resistance in soft dirt. They dig in and act like an anchor.
Oh, because they're thin.
Right. Huge, low-pressure rubber tires actually float over the dirt. They dramatically reduce rolling resistance, which means the tractor can pull a much heavier load of dirt using the same horsepower. And crucially, rubber tires allowed the machinery to move much faster.
Which leads directly to his 1937 design, the Turnipole. I saw pictures of this in the sources. It looks like a giant engine with two massive tires attached to the front of a scraper.
Exactly. The Turnipole was a two-wheeled, rubber-tired prime mover designed specifically to pull his massive carryall scrapers. Because it was on rubber tires rather than steel tracks, it could travel at highway speeds.
He wasn't just moving dirt anymore.
He was moving it incredibly fast over long distances. To give you a sense of his ultimate impact, Letourneau held 299 patents in his lifetime.
That's insane.
And during World War II, his manufacturing company produced 70% of all the earth-moving equipment used by Allied forces globally.
70%.
We are talking about 8,000 massive scrapers, 14,000 bulldozer blades, and thousands of other heavy machines that built the airstrips and supply roads that won the war.
That is a staggering logistical achievement. So let's look at where we are in the timeline. By the 1940s and into the 1950s, we have these incredible, powerful internal combustion machines. We have welded steel scrapers that can hold tons of earth. We have pneumatic tires.
We have the raw power.
Exactly. Humanity finally has the raw mechanical muscle to move mountains of dirt quickly, but that introduces a massive, complex, new problem. The machinery has the muscle, but the machinery is blind. How does the guy driving the tractor know exactly where to move the dirt?
And that dilemma brings us to the 1950s, a period our sources officially refer to as the golden age of mechanical land leveling.
The golden age.
This is the era when the brute mechanical force of the newly developed machinery collides head-on with the grueling, highly precise mathematics of civil engineering.
Because the scale of farming was exploding. Tractor production in the United States hits an all-time peak in 1951, with over 564,000 units rolling off assembly lines in a single year.
The agricultural equipment industry is just booming.
You have companies like Eversman Manufacturing in Colorado building these things called land planes, which are these crazy 40-foot-long specialized scraping contraptions.
The land plane is a fascinating piece of intermediate technology. The concept relied entirely on its extreme wheelbase. Because the wheels were 40 feet apart, as the machine was dragged across a field, the blade in the middle would naturally slice off the high spots and drop dirt into the low spots.
It makes sense when you think about it like a vehicle. It's the exact same physics as why a stretch limousine doesn't feel a speed bump the same way a tiny short wheelbase sports car does.
Exactly. The length of the chassis absorbs and averages out the variations in the terrain.
And alongside those, you have innovations like the one from Gene Hancock, a farmer down in Lubbock, Texas. Around 1950, he invented what became known as the PTO-driven elevating scraper, or the Aggie.
Let's define PTO for the listeners, because that's a crucial piece of farm tech.
Yeah, please do.
PTO stands for power takeoff. It is a spline drive shaft that comes out of the back of a tractor, allowing the tractor's engine to directly power the mechanics of whatever implement it is pulling, rather than just dragging it passively.
Okay, so it's actively moving parts on the trailer?
Right. Hancock used the PTO to power a series of elevator flights, like a conveyor belt, with paddles mounted on the front of the scraper bowl. Instead of relying purely on the forward-pushing force of the tractor to cram dirt into the bowl, The active elevator paddles physically scooped the dirt up and threw it into the back of the scraper,
Which means it required much less horsepower to load.
making it perfect for the average farmer.
So the equipment by the 1950s is highly refined and highly capable. But to return to the bottleneck, knowing exactly how much dirt to cut from a specific spot and where exactly to fill it was the great challenge.
It was the ultimate puzzle.
If you are preparing a field for efficient surface irrigation, you are aiming for an elevation tolerance of roughly plus or minus 1/10 of a foot. That is about an inch.
An inch. Across an entire field.
You can't just eyeball an inch over a 40-acre field. Here's where it gets really interesting, Fry, because the research dives deep into the manual surveying process, detailed in the Soil Conservation Service's National Engineering Handbook from that era.
The SCS handbook.
And reading through this manual, I was absolutely floored by the sheer volume of human labor, physical endurance, and mind-numbing mathematics involved before modern computers or lasers ever existed.
It was an incredibly painstaking, labor-intensive process. Let's walk through what a government or private survey crew actually had to do out in the elements. First, they would go out to a raw, uneven field and establish a physical 100-foot grid.
A physical grid.
They would hammer wooden stakes into the ground every 100 feet in both directions across the entire field.
So if you have a decent-sized field, you are pounding hundreds and hundreds of wooden stakes into the dirt, creating a massive checkerboard pattern.
Yes, and once the grid was established, a crew of 2 or 3 people would spend days walking that grid with an engineer's dumpy level and a Philadelphia rod.
What's a dumpy level?
A dumpy level is a highly precise optical telescope with an internal bubble level mounted on a sturdy tripod. The Philadelphia rod is a tall, wooden measuring stick graduated in feet, tenths, and hundredths of a foot.
So the process looks like this. One surveyor stands at the telescope, making sure the bubble is perfectly leveled. The other surveyor walks to the very first wooden stake, holds the rod perfectly plumb, and the telescope guy reads the exact elevation of the dirt at that specific stake to the nearest tenth of a foot.
And someone writes it down.
Then the guy with the rod walks to the next stake, 100 feet away, and they do it again. Over and over and over for hundreds of stakes, writing down every single number in a leather-bound logbook in the blazing sun.
And the physical data collection was only the first phase. Then came the math.
Oh, boy.
They had to take that logbook back to an office or sometimes just sit on the tailgate of a truck and perform what the handbook calls the plane method of calculation.
Which is what exactly?
This is essentially least squares linear regression. And remember, in the 1950s, this is being done entirely by hand with pencil and paper, maybe a slide rule or a mechanical adding machine if they were lucky.
How does least squares regression actually work in the context of a farm field? How does the math tell them what to do with the dirt?
Well, imagine the field's natural bumpy elevations as a 3D scatter plot of points floating in space. The goal of the plane method is to calculate a single, perfectly flat, tilted plane that passes through that 3D point cloud in a way that minimizes the total distance from all the original natural points to the new artificial flat plane.
So they're finding the average slope.
Exactly. By doing this, they find the average natural tilt of the Earth for that specific field. They had to calculate weighted average elevations for the rows and columns, find the exact mathematical centroid, the exact center of gravity of the field's elevations, compute complex regression coefficients, and derive an algebraic plane equation.
By hand.
By hand.
And the reason they have to do this incredibly complex math is because of dirt economics. You can't just scrape all the high spots off and truck the dirt away. Trucking dirt is ruinously expensive.
It costs a fortune.
And you can't buy clean dirt to fill the low spots. You have to use the exact dirt that is already inside the borders of the field. You want to cut the high spots and use that exact volume of dirt to fill the low spots perfectly.
Exactly. In engineering, it's called achieving a cut-fill balance. And once the engineers spent days doing the math to find that perfect plane, a staking crew would have to go back out to the field, walk to every single one of those wooden stakes on the 100-foot grid, and write specific instructions on the wood with a heavy marker.
So they're writing on the stakes.
They would write things like C2.43, which meant the tractor operator driving over that exact spot needed to cut or lower his blade to remove exactly 2.43 feet of dirt. Or they would write F0.8, meaning the operator needed to fill that spot with 0.8 feet of dirt.
Okay, I have to stop and push back on this because reading the manual, I just could not bridge the gap between the math and the physical reality.
I don't blame you.
How is this physically possible? You have a human operator sitting on a massive roaring steel Caterpillar tractor. The machine is bouncing over rough terrain, the engine is deafening, and he is completely surrounded by a thick cloud of choking dust.
Very thick dust.
How is he supposed to drive past a tiny wooden stake, read C2.43 through the dust, and magically pull a hydraulic lever to adjust a 10-ton steel blade to precisely 2.43 feet while moving at 5 miles an hour?
Your skepticism is entirely justified, because the short answer is it was incredibly, almost impossibly difficult.
I mean, it sounds like guesswork.
It relied heavily on the operator's deep intuition, their visual spatial awareness, and years of hard-won experience. The operator had to constantly watch the stakes, estimate the depth of his blade based on the feel of the tractor's engine lugging, make a pass, and then rely on a surveyor on the ground to constantly check his work and guide him.
So it was just trial and error.
It was a massive feedback loop of human estimation. And to make it even more agonizingly complex, the math the engineers did in the office had to account for a biological soil property called the cut-to-fill ratio.
What exactly is the cut-to-fill ratio, and why does it mess up the math?
It has to do with soil density. When you cut undisturbed dirt out of a high spot, you are aerating it. The tractor blade breaks it up and it fluffs up, taking up more volume than it did in the ground.
Like when you dig a hole and try to put all the dirt back in, but it doesn't fit?
Exactly. But when you drop that fluffed up dirt into a low spot, and a 30-ton tractor with heavy scrapers drives over it repeatedly, the soil compacts. It shrinks tightly together. So 1 cubic yard of cut dirt does not equal 1 cubic yard of filled dirt.
So you have to guess how much it's going to shrink.
Right. Engineers had to calculate a cut-to-fill ratio, typically around 1.2 to 1, or sometimes up to 1.5 to 1, depending on whether it was sandy or clay soil. They had to artificially lower the mathematical plane slightly to ensure they generated just enough extra dirt from the high spots to properly fill the low spots after compaction had occurred.
The math is just relentless. It is honestly a miracle any acreage got leveled to those tolerances at all. And the only reason it did get done on a massive continental scale is because the federal government stepped in once again to provide the financial and intellectual backing. Enter a man named Hugh Hammond Bennett.
Hugh Hammond Bennett is a legendary figure in American agriculture. He is widely known as the father of soil conservation, and he was the driving force behind the creation of the Soil Conservation Service, or the SCS, which is now the NRCS.
And this was after the Dust Bowl, right?
Right. Following the devastation of the Dust Bowl in the 1930s, the government realized that preserving soil and managing water was a matter of national security.
So the SCS builds an entire nationwide network of engineering support. If you were a farmer in the 1950s and you wanted to level your field for better irrigation, you didn't have to hire an expensive private engineering firm.
No, the government would do it.
The SCS would send out these highly trained engineering crews to do the surveying, the least squares regression math, and the physical staking of the field entirely for free. And beyond that, under the Agricultural Conservation Program, the government actually subsidized the physical earth moving. They paid farmers up to $3,500 a year to hire the heavy machinery and do this essential leveling work.
That was a tremendous amount of money in the 1950s, easily covering a huge portion of the capital cost for a farmer. And the environmental payoff for the nation was undeniable. The research data shows that precision land leveling saved massive amounts of water, preventing roughly 35 to 40% of the agricultural runoff that was previously happening on uneven fields. But
there is always a but. When we alter nature this aggressively.
There really is.
Yeah.
This raises an important question, one that scientists at the time were acutely aware of. What is the biological cost of all this mechanical violence? While leveling saved water and improved irrigation efficiency, the 1950s SCS literature and much later long-term studies, like a prominent one published by Bry in 2006, documented a major ecological contradiction.
Which was?
When you take a heavy scraper and scrape 2 or 3 feet of soil off a natural high spot to drag it into a low spot, you are completely destroying the natural soil profile.
Because topsoil isn't just generic dirt. The top few inches are where all the organic matter, the microbes, and the nutrients live.
Precisely. You are scraping away the fertile, nutrient-rich topsoil horizon and exposing the dense, dead mineral subsoil underneath.
So you're basically spreading dead dirt.
The agricultural literature heavily warned that these major topographical changes almost always severely reduced crop production in the cut areas of the field. The biological health of the soil was ruined until farmers could artificially replace the lost fertility, which usually meant massive, expensive applications of synthetic chemical fertilizers.
Wow.
It was a stark ecological trade-off. Farmers gained absolute control over water efficiency, but they temporarily destroyed the soil's natural health in significant portions of their fields.
Let's recap exactly where we are in the timeline, because the tension is peaking. By the late 1950s and early 1960s, the industry has pushed the current paradigm to its absolute breaking point. We have the heavy internal combustion machinery, we have the government funding and the engineering support.
And we have the grueling, complex mathematics.
But the math takes too long to do by hand. The physical staging of the field is incredibly labor-intensive and slow. The soil profile is getting disturbed by multiple inefficient passes of the scraper, and the tractor operator's eyes and reflexes, no matter how skilled, just aren't perfect enough to hit a 1-inch tolerance through a cloud of dust.
They're human.
The entire earth-moving industry was practically begging for a way to automate the blade. And the answer didn't come from Caterpillar or John Deere. It came from a high-tech workshop in Ohio, courtesy of a spinning beam of light.
The transition into the 1960s brings us to the absolute technological turning point in this history, the laser revolution. And the narrative centers on an engineer named Robert H. Studebaker.
Studebaker.
Studebaker co-owned a business called Process Equipment Company, located in Tipp City, Ohio. They were not a farm equipment company. They were a highly advanced metal forming and engineering firm doing ultra-precise work for the automotive giants like Ford and GM.
And the National Nuclear Labs.
Yes, manufacturing components for Los Alamos and Oak Ridge.
Which means Studebaker was a guy deeply accustomed to working with extreme microscopic tolerances.
Very much so.
And the story goes that around 1964, a large, frustrated, earth-moving contractor came to his Ohio workshop with a plea. The contractor was tired of the stakes. He essentially asked Studebaker, is there any way, using modern technology, to build an elevation control system for my graders that completely eliminates the need for all these wooden stakes, the surveyors, and the string lines? We are wasting an immense amount of time and money on human error.
And Studebaker took up the challenge. He teamed up with a salesman from the Perkin-Elmer Corporation, a major optics and technology company, and together they achieved a massive, world-changing breakthrough.
Wow.
Studebaker's invention was ultimately awarded U.S. patent 3,471,234 in 1969. To understand how revolutionary this patent was, we have to look closely at the physics and the specific components he employed.
I would love to dig into the physics here because looking at farm equipment from the 60s suddenly integrating lasers feels like science fiction arriving in a cornfield. How did it actually work?
Well, Studebaker decided to use a helium neon gas laser, often referred to as a HENE laser. This was incredibly bleeding-edge technology at the time, only invented a few years prior.
Why helium neon?
Why use a helium neon gas mixture instead of the earlier ruby lasers? A ruby laser pulses light. It flashes. You cannot use a pulsing light to guide a continuously moving tractor because the hydraulic blade would jerk up and down with every pull.
Well, that would be terrible.
Right. A helium neon laser, however, provides a continuous, steady wave of light. Crucially, it also emits light in the highly visible red spectrum, specifically at 632.8 nanometers. That visible red beam was vital for the engineers to see what they were doing during the initial setup and calibration in the field.
Okay, so he has a continuous red laser beam, but a laser is just a straight line, like a pointer. How does a single straight line help grade an entire 40-acre field?
That is where the genius of the engineering comes in. Studebaker took that straight laser beam and projected it straight up into a motorized spinning pentaprism.
A pentaprism.
He sourced this specialized prism from the Brunson Instrument Company. A pentaprism is a complex, five-sided reflecting glass prism used in optics to deviate a beam of light by exactly 90 degrees, regardless of slight misalignments.
Oh, okay.
So as an electric motor spins this prism at a high rate of speed, that single vertical laser beam is bent 90 degrees and swept outward in a rapid, continuous 360-degree circle.
The analogy that helped me visualize this perfectly is thinking of it like a perfectly flat, invisible ceiling of red light hovering over the entire field.
Yes.
Or even better, think of it like a rapidly spinning lighthouse beam sweeping across the landscape. But instead of warning ships, it is establishing a perfectly constant mathematical elevation reference over the dirt.
That is exactly how it functioned. It created a perfect, weightless reference plane of light.
Yeah.
So the process changes entirely. You place this laser transmitter on a tall tripod in the middle of the field, set your desired slope, and turn it on.
And then what about the tractor?
Then you look at the tractor. On the tractor itself, you mount a tall steel mast extending up above the scraper blade. On that mast, you mount a photoelectric receiver. This receiver is packed with sensors that detect exactly where that invisible plane of laser light is hitting it.
And this is the crucial part. The receiver doesn't just beep a little horn to let the driver know if he's too high or too low. It actively takes over the driving of the blade.
Yes. The receiver translates the light strikes into electrical signals, and it sends those signals down cables directly into the tractor's hydraulic servo valves.
Which are insanely strong.
Extremely strong. By the 1960s, these industrial hydraulics were operating at incredibly high pressures, up to 3,000 pounds per square inch. So hundreds of times a minute, the photoelectric receiver reads the laser light and tells the hydraulics to automatically raise or lower the heavy steel blade instantly.
Keeping it perfectly aligned with that invisible plane of light.
Exactly.
Yeah.
The human operator just puts the tractor in gear and drives forward. The laser and the hydraulic feedback loop do all the grading perfectly, dynamically, without a single wooden stake in the ground.
It is brilliant. It completely removes human reaction time and guesswork from the equation.
It does.
But like all bleeding-edge first-generation technology, the commercial reality in the late 60s was a bit rough. The research notes that bringing this sci-fi tech to the dirt was wildly expensive and fragile at first.
Oh, very fragile.
Those early helium neon lasers cost between $7,000 and $8,000 each, which was the price of a house back then. And the delicate glass plasma tubes inside them burned out after just 300 hours of use.
Not to mention the power requirements.
Right, you had to drag a heavy external AC power generator out into the dusty field just to run the transmitter.
But despite the initial exorbitant costs and the fragility of the glass tubes, the productivity gains were so massive and undeniable that the technology could not be ignored. Studebaker and a partner named Ted Teach founded the Laserplane Corporation in 1967 to commercialize the system.
And the competition jumped in, too.
Competitors recognized the potential and sprang up quickly. Companies like Spectra Physics out in California and AGL in Arkansas. It is also important to note that this wasn't purely a private industry endeavor.
The USDA was involved.
Simultaneously, over at the USDA Agricultural Research Service, a government scientist named Dr. James Foss at Ohio State University was pioneering similar laser control systems, but his focus was on guiding trenching machines for installing subsurface drainage pipes perfectly on grade. The technology was proving itself rapidly across multiple agricultural disciplines.
So lasers proved they could work on construction sites and specialized drainage projects in the late 60s. But how did this expensive, delicate technology actually reshape the economics of the everyday American farm?
Let's talk about the harvest.
Yeah, the real-world outcomes and agricultural impact of all this innovation as it transitioned out of the lab and into the fields in the 1970s.
The adoption of laser leveling by the agricultural sector fundamentally altered both the economics and the environmental impact of farming. Let's look at specific documented regional impacts. In Arkansas, for example, the research highlights the work of Isbell Farms.
They grew rice, right?
Yes, they used lasers to pioneer something called zero-grade rice farming. Because rice grows in standing water, you want the land as flat as a billiard table to maintain an even water depth. Using lasers, they were able to grade their fields so perfectly, mathematically flat, that they achieved a massive 30% reduction in water use.
30%, that is a massive volume of water saved just by letting a beam of light do the math instead of a guy bouncing on a tractor seat trying to guess the grade.
It really is. And we see similar efficiency numbers out west in California. In the Sacramento Valley, a 1970 study by an agricultural researcher named Wick documented that precision laser leveling in rice paddies led to a direct 10% increase in actual crop yields.
Because no crops were drowning or starving.
Exactly. Furthermore, it created a 12 to 15% gain in equipment efficiency, simply because the tractors and harvesters weren't fighting uneven terrain, sinking into low mud spots, or breaking axles in dry ruts anymore.
But the economic impact is perhaps most stark when we look at regions where water is a severely limited resource, like Texas.
The Texas High Plains.
Right. They rely heavily on the Ogallala Aquifer. This is a massive, ancient underground water source that was, and still is, facing severe depletion from overpumping.
So every drop counts.
Farmers in the High Plains had to make absolutely every single drop of water count, or they would go out of business. The initial capital cost of hiring a contractor with a new laser-guided scraper system was steep between $150 and $500 per acre in the 1970s. But the long-term math proved it was an essential investment.
It paid for itself.
Research showed that just a 10% increase in irrigation efficiency netted a Texas farm an additional $1,284 annually on a standard 160-acre spread. The expensive laser system paid for itself rapidly by maximizing the value of every gallon of pumped water.
When you look at all of this together, the sheer scale of the engineering is humbling.
It really is.
If we connect this to the bigger picture, you really see the culmination of a massive, sweeping historical arc. 6 millennia of grueling human effort, from the back-breaking, muddy hose in ancient Mesopotamia to the geometric ingenuity of James Porteus's Fresno scraper.
To the massive welded Latorno earth movers of World War II.
Yes, and the agonizing handbook math and physical staking of the SES engineers. All of it converged in that Ohio workshop in the 1960s. The foundational inventions of the continuous laser transmitter, the sensitive photoelectric receiver, and the high-pressure hydraulic feedback loop completely eliminated the wooden stakes, the complex hand calculations, and the human guesswork.
It's incredible.
They permanently, fundamentally altered the agricultural landscape of the planet. It is one of the quietest yet most profound technological revolutions of the 20th century. We removed human error from the physical shape of the Earth.
So what does this all mean for us today? I ask you, the listener, to really think about this conversation the next time you drive past a farm, or even the next time you sit down to eat. Think about the sheer scale of engineered perfection required just to bring a simple plate of food to your table.
You're not just looking at dirt.
You are looking at one of humanity's most hard-won, scientifically complex engineering triumphs, hiding in plain sight as a flat, quiet field.
And to leave you with a final, somewhat ironic thought regarding the future of this technology. If the 1960s gave us lasers to perfectly flatten the Earth to a strict, rigid mathematical line, today's technology is actually taking a radically different path.
Wait, really? We're not doing flat anymore?
Well, the modern descendants of Studebaker's laser systems now use RQK GPS and highly detailed satellite topography to guide the tractor blades. And they use these tools to grade fields not to a perfect artificial flat plane, but to complex undulating 3D models that are specifically tailored to the Earth's natural curvature and natural microdrainage patterns.
So they're putting the curves back in.
Yeah, exactly. If we spent 6,000 exhausting years trying to force the Earth to be perfectly flat, what does it mean for our future that our ultimate technological achievement is learning how to intelligently put the curves back in?
That is a deeply fascinating full-circle place to leave it. Thank you so much for joining us on this deep dive. Keep looking beneath the surface of the everyday world around you, because as we've seen today, there is always a massive hidden story waiting right there in the soil.